When we talk about building materials, our minds usually jump to things that are manufactured: concrete, steel, bricks. But what happens if we start with the ground itself? I mean, not just as something to build on, but as the primary material we build with. To really get that, you kind of have to shift your perspective. Think less like a builder and maybe a little more like a geologist.
And that brings us to this really fundamental premise that the soil under our feet, it isn't just random stuff. It has a history, it has an origin story, and that story is what dictates all of its properties.
So, the concepts we're going to walk through here are based on the work in The Memory of Rock, Understanding Rammed Earth by Gokul Salvadi. It really explores this deep connection between geology and construction. And the whole thing starts with, well, redefining the material itself. Okay, so the first thing we have to do is get our terms straight. When we say soil in this context, we're not talking about the dark organic topsoil in your garden. We're talking about subsoil, the stuff you hit when you dig down a foot or so. And it's really just weathered rock. The quartz in it is still quartz, the feldspar might have broken down into clay, but it still holds the same basic chemistry of its parent rock. All that's happened is that the rock has dispersed. All right, so that's the big question, right? How do you take this loose, dispersed material and actually turn it into a solid structural wall? Well, the process is called consolidation, and it really happens through two different actions that are working together at the same time. First, on the macro level, what you can see, you have what's called mechanical interlocking. So think about the sand and gravel in the mix. These aren't perfectly round little spheres. They're angular, sharp fragments of rock. When you compress them, all these edges and faces lock up against each other. They create this really stable interlocked structure, but that's only half the story. The other crucial part of its strength, well, that happens on a microscopic level, and it's all about the clay. And this is the part that might not be so obvious at first. Clay isn't just some passive filler that's taking up space. It's an active binder. The whole process hinges on getting the moisture and the pressure just right and applying them in a very specific sequence. Okay, so picture this. In its loose state, clay particles are like these teeny tiny flat plates, and they're all just jumbled up, pointing in random directions. The first thing you do is add just enough moisture to make the soil damp. This creates these super thin films of water around each little platelet, which basically lubricates them and lets them move around. Then comes the compression, the ramming. You're physically forcing those platelets to line up face to face. And as you apply that pressure, you're squeezing out any excess water, making those water films thinner and thinner, until the platelets get so close to each other that these powerful electrochemical forces can just take hold. And the specific forces we're talking about here are capillary tension, that's from the little bit of moisture that's left, and more importantly, something called van der Waals forces. Now, these are the exact same weak interatomic forces that, when you add them up over millions and millions of particles, are strong enough to hold layers of rock together deep in the Earth's crust. So you see, you haven't actually added a chemical binder like cement. You've just arranged the particles so closely that physics can do the work. So, when you think about it, this whole process isn't new at all. It's exactly what nature does over millions of years to turn loose sediment into solid rock, just using the immense pressure of all the layers above it. All rammed Earth does is take that exact same mechanism and speed it way, way up, applying in a few hours what geology takes eons to accomplish. Okay, so understanding the mechanism is one thing, but what does this actually mean for performance? Just how strong is this stuff? Let's put some numbers on this to get a feel for it. The walls of a typical one-story house, they need to support a load of around 1 megapascal. Now, a standard, unstabilized rammed earth wall can handle about 3 to 5 megapascals of compressive strength. And if you stabilize it, usually with a little bit of cement, that number jumps up to 10 to 15. So right away, you can see the material is much, much stronger than it needs to be. And it helps to compare it to some other materials we're all familiar with. Unstabilized rammed earth, it's right there in the same strength range as a standard fired clay brick. And stabilized rammed earth is right up there with low-grade concrete. The takeaway here is that this is not some kind of weak or fragile building method. So let's just take a typical number, say 10 megapascals for a stabilized wall. That means it's carrying the load it needs to at only a tiny fraction of its total capacity. The material isn't straining at all, it's operating well within its comfortable limits. And this brings us right back to where we started, back to geology. Because the performance we were just talking about, it isn't the same everywhere. It depends completely on the parent rock that the soil came from in the first place. So, for example, if your soil comes from granite, you'll probably have stable clays and a good amount of quartz sand, which makes it really predictable and great for ramming. But soil from basalt? That might have more expansive clays, the kind that swell and shrink with moisture, and you have to manage that carefully. Then you have things like laterite soils, which are rich in iron and are often naturally pretty strong just as they are. So, in a way, the geology of your site is basically the spec sheet for your main building material.
So, really, the whole transformation is just about assembly. You start with loose, unconsolidated soil. It's full of air, the particles are all over the place, and there are no bonds holding them together. And you end with a dense, consolidated mass, where the larger particles are interlocked and all the little clay platelets are bonded together. And this really gets to the core idea. Think about a pile of loose bricks. It has zero structural integrity. But that's not because brick itself is a weak material, right? It's because the bricks haven't been assembled into a wall. The exact same thing is true for soil. Its weakness in a loose state is just a state of disorganization. The act of ramming is what assembles it. It takes the strength that's already there in all those dispersed rock particles, and it just organizes them into a stable, load-bearing structure. The difference isn't because of an additive or some new chemical reaction. The difference is consolidation.